double slit experiment. So this experiment is set up where there is a source of something. And that source could be light. It could be electrons. It could be alpha particles, okay? But it's the source of whatever it is you're interested in studying, okay? So over here, let's first think about what would happen. You know, we could think about anything that we really understand in life to behave as a wave. So that could be light. It could even be water. All right, so let's think in terms of that. Something we're really familiar with. And so there's our source. Okay, so the double slit experiment works like this. Imagine that this is a barrier. This is a wall. And this wall or barrier, I'm hoping you can tell that there are these holes in the wall, right here and right here. Okay, so we've got a hole here and a hole here. So what that means is our source, and let's imagine that these are waves coming out. And so let's draw waves like how we imagine water waves. If we're looking bird's eye view and we've dropped our pebble, and then we are now seeing waves ripple out in a still pond, right? Okay, so this is what we're imagining here. If this were a light and that's coming out, and we're looking bird's eye view, then we're looking at the crests of those waves when I draw this line here. Okay, so then what happens? Well, when it hits the wall, and this is easier to imagine if it's water, what does it do? Hits the wall, sloshes back, right? So hits the wall, sloshes back. So that's not going to keep passing on through, but think of this little part of the wave that's coming up to this slit, and it can go through. So that's essentially like another little source, right? So the wave came through, and then now it's propagating out from there. Same with this hole here, or this slit that's made in the wall. Same thing, we've got this. So now look at what is happening. Okay, so what happens when we have the crest of one wave that crisscrosses with the crest of another wave? Does the wave get bigger or smaller? It gets bigger, yes. So amplitudes are additive. So it's something about waves. If they're lined up, additive. All right? So right here, anywhere where it overlaps, we're going to get a larger amplitude. And then we have other possibilities where there is the trough of the wave, okay, that's going to get deeper. And then we have where they cancel each other out, right? We have a crest lined up with a trough, and they flatten out, and there's zero amplitude. Okay? So we're going to have, what's happening in here is this interference pattern that occurs. And so ultimately, if you're able to, we have these waves coming out like this, and then they're starting to interfere with each other, is that your detector screen over here, if we're talking about if this is light, then you could even have a type of detector screen that's similar to something you'd use in photography. Something that changes when a photon hits it. When light hits it, changes color. All right. If we're looking at water, that's something we probably have to watch it with cameras and see the waves going up and down and things like that. So this experiment's a little bit easier to detect with light than with water, and to see what happens here. And ultimately what you see is over here is this interference pattern. So it looks something like this, where they get bigger and smaller. Not exactly like this. It's much more symmetric than what I've drawn. But the point is, there's an interference pattern. This is what you see when you have something that's a wave source. Okay? Now, let's imagine if we have something that is a known particle source. All right? So, like Nerf balls, right? If you're like shooting your Nerf gun, all right? So that's going to be our source here, where let's look at something where it's, instead of known wave behavior, particle behavior. Particles. So now, same thing. If you have this wall, but the wall has the two holes in it, and here you're shooting these Nerf balls. Okay, they're going to hit the wall, they're going to bounce back. Same thing if it was, one of those tennis ball shooter things, to practice with. Okay, same thing. Hits the wall, bounces back. But if it goes through one of these holes, it will continue on its trajectory and it will hit our detector screen over here. Okay. So now what will this detect? If its job is, this detection apparatus here, if its job is to detect wherever something hits it, then we would expect here to see nothing, 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 something. And in fact, a lot of them, if that's shooting a lot of them, it's going to be a large peak there. And then nothing, 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 and then another peak there. Okay, so if we inspect these two possibilities, we've got what we expect to see if it's a wave, and what we expect to see if it's a particle. So now, do the experiment with electrons. Do the experiment with electrons. And what do you see? If we were thinking about electrons as matter, as particles, then of course we would get the result of there just being these two peaks here. But guess what was seen in the Young's double slit experiment? Waves. Those electrons were interfering with each other because they were exhibiting their wave-like properties. Isn't that a trip? And I know that was like we went through a lot, but just to show that yes, it has been confirmed many times over in many ways that electrons do exhibit wave-like properties. All right?